it is part 2 of section 5.2, metric similarity and the diagonalization theorem. A and B are two n by n square matrices. Then A is similar to B if there is an invertible matrix P such that A is P, B, P inverse, or equivalently, P inverse A, P is B. If we define Q as inverse of P, then this equation can be written in this form. So we can say B is also similar to A. So the similarity is a symmetric definition. So we can say simply A and B are similar. The mapping A to P inverse AP is called similarity transformation. Okay, this theorem is explaining and how to get the characteristic polynomial through the similar matrices. Okay, and if m by n matrices A and B are similar, then they have the same characteristic polynomial and therefore the same eigenvalues. The eigenvalues must be exactly the same. Let's prove that. B is similar to A, so B is P inverse AP. Then now B minus lambda I can be written here, that is B minus lambda I. Now for this I, we use P inverse P. Then we factor P inverse, now P to the right. Okay, so we reach at P inverse A minus lambda I and P. Now we apply determinant. And determinant this one is same as determinant of that, but a property of determinant is that the determinant of metric product is the same as the product of each determinant. So here, determinant of B minus lambda I can be written the determinant of P inverse, determinant of A minus lambda I, determinant of P. But now this one is reciprocal of that, so we can cancel out so that we end up with determinant of A minus lambda I, which means that once A and B are similar, then they have exactly the same characteristic polynomial, so that their eigenvalues are exactly the same. Okay, here, diagonalization. When n by n matrix A, square matrix A, is diagonalizable if there is an invertible matrix P and diagonal matrix such that A is PDP inverse. That means that A is similar to diagonal matrix, then A is diagonalizable. Once it is diagonalizable, so similar to a diagonal matrix, then sometimes it is really quite efficient in the computation of the power of the matrix and determinant of the matrix. Okay, here A is diagonalizable, then A is PD, P inverse with a diagonal matrix D. Then A squared, A and P inverse P will be cancelled, and that D squared. So we can get this term using the same idea. the power, general K power of A can be obtained in this way. P d to the K, P inverse. Once the given matrix is diagonalized, then simply power of A can be obtained by powering the diagonal matrix, which is very simple. Now, how about inverse? Also, if you take inverse of the diagonal matrix, then we can get the inverse. Of course, the given matrix must be invertible when we get this one. Now, determinant of A is same as determinant of D. Earlier, we proved here, once A and B are similar, then now determinant must be the same. Okay. Now, we choose here lambda equals 0, so then exactly here, determinant of B is the same as determinant of A. Okay. Now, we have a self-study problem. Now, for the given matrix, and P and D are given, so that here now A is similar to D, and A to the K. You can find a formula for A to the K. So first make a kth power, and D to the K is 5 to the K, 3 to the K, and you can multiply P and P inverse from both sides, and you can find the final formula. Okay, that is this one. You can check it yourself. Here we have the diagonalization theorem. When n by n square matrix A is diagonalizable, which means it's similar to a diagonal matrix, if and only if A has n linearly independent eigenvectors. So for diagonalizable matrices, it has always n linearly independent eigenvectors. And in fact, A is written as P d P inverse if and only if the columns of P are n linearly independent eigenvectors of A. In this case, the diagonal entries of D are the corresponding eigenvalues of A. Here we collect the n linearly independent eigenvectors to form the matrix P, and we form a diagonal matrix using the corresponding eigenvalues, lambda 1 to lambda n. Here now, AVK is lambda k vk. So lambda k vk are eigenvalue, eigenvector pairs. So it must be matched, the order must be the same. Then we can write here A is P d P inverse. So once it is diagonalizable, then always we can put this way, and this is only the way. So P will be the collection of eigenvectors, and D is diagonal matrix of the corresponding eigenvalues in the same order. Okay. Here is the proof. If you are interested in mathematics, then you can read it. Okay. Diagonalize the following matrix if possible. That means that we have to check if it has 3 linearly independent eigenvectors. Okay, the solution is here. First, we try to find the eigenvalues and try to find the 3 linearly independent eigenvectors, and we can construct P by using the eigenvectors, and we can construct D from the corresponding eigenvalues. That's the the order. Now here we did it in this way. Now if you are using computer program in MathTalent, and for A, now by using EIG, built-in function, you can get the P, that is collection of eigenvectors, and D is the diagonal matrix of corresponding eigenvalues. So we print out, okay, P and D, and we check here P inverse is the given matrix. So it is the same, 1 minus 3 minus 3, okay, 3 minus 5, 3, okay, it's the same, 3 minus 3, 1 for the last column, okay, it's the same. Now here, once you try to get eigenvalues and eigenvectors by hand, then you'll get 1, minus 2, minus 2, so that we have two eigenvalues, 1 and minus 2, and minus 2 have two eigenvectors. Okay, now for lambda is 1, okay, it's okay, here scaled. Now if you multiply some scalar, then you can reach at 1, minus 1, 1, and 1. So same magnitude in modulus, so that you can get this one. But now for lambda is minus 2, we have this one, and this one, two eigenvectors, but the computer output is quite different. Okay, and here let's check if it is correct. Okay, now start with lambda is minus 2, then a minus lambda I must be same as a plus 2i. That is the same here. Along the diagonal, we add 2, so that there is 3, 3, 3, and minus 3, minus 3, minus 3, again 3, 3, 3. So we have to solve here this matrix times x equals 0. How? By using the elementary row portions. Okay, from A, we're ignoring the 0 extra column. Okay, here after scaling, we have 1, 1, 1, again 1, 1, 1, again 1, 1, 1. So essentially they are the same. So that we have here zeros. That means that, I'm sorry, x1 is the basic variable, and x2 and x3 are free variables. From here now, x1 equal minus x2 minus x3, and x2 and x3 are free variables. So we have x2 is x2, x3 is x3. So the vector x can be, along with x2, the direction is minus 1 and 1, 0, and along with x3, now here direction is minus 1 and 0 and 1. This one, that one is exactly this two. So for arbitrary choice of x2 and x3, x will be the eigenvector. Now using 1 and 0, we have that one, and now 0 and 1, we have this one. And now we have, these are linear independent, so that this can be two eigenvectors. But here, the computer output is quite different. Now I checked here, this one can be made by a linear combination of these two vectors. So this column, that column makes a matrix, and that is the right hand side, and try to solve the problem. then you can solve n, which means that this is on a linear combination of these two vectors. Again, for this last one, you can do the same, so that this is a linear combination of these two, so that, and these are linearly independent, so that either you can use these two or these two. It doesn't matter. It'll be the same anyway, because now the same eigenvalue, you can get various other vectors rather than this hand-computed vectors. Okay, but essentially they are the same. Okay. Okay, that's the end of section. Thank you.